Okay, we'll just continue with the inverter working principle as already explained in the previous video. This is how the working principle of an inverter goes on, and this is the basic symbolic representation of an inverter, and this is the truth table. A is the input, Y is the output. When the input is 0, the output is 1 because it is always a complementary output. That is how A is equal to Y bar. Y is equal to A bar. If input is 1, the output is 0. If the input is 0, the output is 1. So let us now look at the principle of working when input A is equal to 1. And as I have already told you, this is your VDD, this is your ground, high potential VDD, and ground is your low potential. So always the current tries to flow from high potential to lower potential. So always the path of the current is from the high potential to low potential. So when the path is chosen like this, it encounters two devices. One is the PMOS transistor and the other one is the NMOS transistor. And in an inverter, this is how the connection is given. They are neither in series nor in parallel. It is just, that is the reason I told you in my previous video that a CMOS inverter is a combination of NMOS and PMOS. What combination is it? It is not in series. So the two gates are connected together and you have a single input. The two gates, gate of PMOS and gate of NMOS, are connected together and together they form a single input because input is always given at the gate terminal. And the output, so this is your output. Y is the output. And where is the output taken? If you notice the CMOS inverter, because if you look into this, let me show by drawing it properly. Just a moment. If you look at this, let me first take, alright, let me show you the combination of CMOS inverter. Let me now take an NMOS inverter. So in an NMOS inverter, this is how the representation of NMOS device is. So this is your gate, all of us know. And similarly, let me take, as I have already told you, in CMOS, always the PMOS devices in the pull-up region. So this is the representation of bubble, and always PMOS device is connected to the supply, and the supply is known as drain VDD. See, VDD, and this becomes your ground, which is shown as V source and substrate. So this is positive potential in other words, and this becomes your negative or ground. Alright, now these two devices. Now gates, the two gates are shorted together. So the two gates are shorted together and this in turn becomes your input. So this in turn becomes your input. The input here in turn is represented with A. That is what I have shown you here. Next, you have NMOS device. Now what are these terminals? What are the three terminals of the MOSFET? Gate, source and drain. Already we are connected with gate. The two gates are connected and shorted together to get a common input, which is given here as A. Now which is the source, which is the drain? And this is the fancy of NMOS and PMOS. Always please remember, NMOS and PMOS are complementary in action. So at the initial cost, always the source of PMOS is connected to VDD. The source of PMOS is connected to VDD. And similarly here, the source of NMOS is connected to ground. If source is connected to high potential, the reverse should happen in NMOS. Therefore, the source is connected to low potential here. Then the leftover terminal is your drain. So the leftover terminal is your drain, and this is the place where they form a junction, and this is the place where normally the output is taken. So please remember, in CMOS structure, always the output is taken at the drain junction. The output is taken at the drain junction. So this is how you have to remember the construction of a CMOS inverter. Now let us justify whether this truth table works or not. Alright, when A is equal to 1. Alright, this is okay. If this is okay, we'll go on with the next skeletal structure. Let me show how the CMOS inverter works in my next slide. Meanwhile, just a moment, we'll drop right now. I'll go to the next slide. shortly. Let me show the representation of how the truth table is satisfied here. And if the truth table is satisfied, this circuit behaves as an inverter. And I've already told you that NMOS and PMOS are merely switches. So this is your VDD, this is your VDD, and this is your ground or VSS. Ground or VSS, both representation are one and the same. So this is the place for my PMOS circuit, and this is the place for my NMOS circuit, because they are just behaving like a switch. So as you look into this, this becomes your gate. So this representation is your gate, and the two gates are shorted. So the two gates are shorted here, right? Now when you look into this, or not at all to consider, you can still ignore this. You can still ignore this connection. You can still ignore. You can show the representation like this. This is gate and this is gate. Alright. Now let us look. Initially, when A is equal to 1, when A is equal to 1, what happens here? When A is equal to 1, 1, and what is this bubble? Bubble represents the 0 representation. 1 becomes complement. So what is the status of PMOS device? Gate is open. If the gate is 1, when you try to close it, obviously at that junction, when it is 0, the reverse should happen in your complementary version. Therefore, your PMOS is off. Your PMOS is off when the input is A. Similarly, what happens here? When A is equal to 1, the gate which is now open will become closed. The gate which is now open will become closed. So your switch is now connected. Your switch is now connected, or you can also show it like this. You can also show it like this. This initially was your switch. Now the switch is shorted. Now the switch is shorted. Initially this is the switch, now it is connected. Now it is connected. So what happens to this device? It is on. Now what is the output? Output is always taken at the drain junction. So let me call this as V0, or in other words, this is also nothing but your Y. I can also consider this as Y. If that is the case, let me remove this, because this is your output. What was the input given? When A is equal to 1. When A is equal to 1, this is an open circuit, this is a short circuit. So what is the potential value at Y, which is the drain junction? VDD, high voltage, 5 volts. It comes here, it encounters an open circuit. So no voltage flows in this junction. No voltage flows, and as a result, what is the value at this point? Y is equal to 0. Because in the initial case itself, you find an open circuit. In the initial case, you find an open circuit, therefore Y is equal to 0. Therefore, when A is equal to 1, what is the output? 1. 1 complement is Y. Is that satisfied? Yes. So this truth table is satisfied. Similarly, on the same grounds, I have to check with the second input 0. So in that case, if I want to check with the second input, I have to just work with second case. So what is the second case? The second case is like this. Second case, yes, this is the ideal condition of how the initial device looks. Next case, when A is equal to 0. A is equal to 0. What will be the status in PMOS? A is equal to 0. 0 bar is 1. So this is on. So PMOS device is on. A is equal to 0. 0 bar. Therefore, this status is open circuit. Therefore, the bottom device is off. Now, irrespective of the status of the devices, I am keen on checking what is the status of the input, Y. So what is the status of the input here? What is Y? Y in turn is equal to, if I give 5 volts as the supply, if I give 5 volts as VDD, entire 5 volts will come here. It encounters a short and the 5 volts will flow here. Always, that is how the strategy of every potential is. It has to reach to the ground. So it tries to reach here. It comes here, it tries to reach here. It encounters an open circuit. So there is no path for 5 volts to go to the ground. And at that moment, when you check the voltage here, this will be 5 volts itself. So the voltage here is 5 volts. When we talk in terms of logic, it is nothing but 1. Therefore, initially when your input is 0, the output is 1, and that is how the truth table condition is. So, this ideally, this combination by constructing a PMOS on the pull-up region and by constructing an NMOS in the pull-down region behaves as an inverter. Hence the proof. Therefore, this is your ideal CMOS inverter. So, with proof you have to check. With proof you have to check is only with the justification of the truth table. So, this is the conclusion of a CMOS inverter. Let us now go to the representation of transistor symbols. By now you are very much familiar that this is your NMOS enhancement and this is your PMOS enhancement. Why P? Because there is a bubble. Now I have to show you the depletion, right? What is depletion? Channel exists during construction itself. So the representation of the depletion is shown here. This is one way of representation. Most of the textbooks follow this representation. There is also another representation of depletion. Multiple textbooks have their own. So please, we will stick on to one kind of representation. So depletion can also be shown like this. Depletion is shown like this. Same way, you can also consider this as drain, source and gate. This is one way of representation, and arrow direction also is shown. So you can either stick on to this or you can make it dark. Darken this region as shown like this. This is also the representation of depletion. Both are one at the same. So these are the commonly used representations. If you notice here, G and I are the most commonly used symbols in VLSI logic circuit. So if you look into this representation, these are the different representations. N region is at higher potential voltage is the drain in PMOS. Yes, lower voltage is the drain. Yes, just now I have shown you. In N region, drain is always at the higher potential and always the source is connected to the ground. Reverse should happen in PMOS. In PMOS, source is at the higher potential, drain is at the lower potential. MOS devices are symmetric. So this is the normal representation. When you notice here, the current flow is inwards, the current flow is outwards. So this is also one representation or differentiation between NMOS and PMOS. In NMOS, the current flow is inwards, whereas in PMOS, the current flow is outwards, away from the substrate. That is why the arrow mark is shown in outside and in NMOS it is inside. So these are the representations. Not to worry, please stick on to one representation, but not to panic when these kind of questions appear in different formats. It can be your VTU question paper, or it can be your GATE paper, or it can be any DRDO exam or ISRO exam. It is not necessary for you to be panic. You should be aware of how the various representations are present for different devices like NMOS and PMOS. All are one at the same. For simplicity, we have shown you the simple structures. So this is also one way of representation. Please look here. The arrow is shown here at the source terminal. This is also one way of representation. So please keenly you can watch at this later on. At this point, you can just ignore this representation. So with this we complete the first part of module 1, and next we go with MOS transistor theory. So what exactly we discuss in MOS transistor theory is introduction, long channel IV characteristics, non-ideal IV effects and DC transfer characteristics. So we'll have a discussion on this. Before that, we'll go into the introduction. So when you look at this, yes, these are the different various symbols representations. Figure shows some of the symbols that are commonly used for the MOS transistor. Yes, here you can see the arrow here, inwards arrow, outwards arrow. This is your NMOS. NMOS can be equally represented like this. NMOS can also be represented like this. PMOS can be represented like this as well, this as well. So arrow inwards here at the source. These are the representations. This is outside. Arrow is outside. The various representations. Yeah, now we go into the introduction. In an NMOS transistor, the majority charge carriers are electrons, as I already told you. In PMOS transistor, holes are the majority charge carriers. So here, this is how the representation of a MOS structure is. So the top layer is a good conductor called the gate. Yes, you look into this. This is your semiconductor. Yes, this is your oxide, the thin layer. the thin layer is your oxide, and above that you have your metal, which is polysilicon, which is normally your gate. So this represent your MOS circuit, and transistor gates are now made of polysilicon. Okay, polysilicon, what is polysilicon? Silicon formed from many small crystals. So polysilicon is nothing but a just a mutated version of silicon. All of us are playing with silicon itself. And the middle layer is a very thin insulating film of SiO2 called the gate oxide. So when you expose this silicon to the atmosphere, the oxygen elements or molecules or particles get reacted and a thin layer is grown by itself. So this is silicon oxide. And the bottom layer is the doped body. It can be N type or P type. So here right now P body is shown. That means it is NMOS. Always please remember, NMOS device means it is constructed on a P substrate. It is constructed on P. Whereas if you have a PMOS transistor, if you have a PMOS, it is constructed on N. PMOS is constructed on N. Let me write this clearly. So PMOS is constructed on N. So this is how we have the representation for NMOS. And if you see, the figure shows a P body in which carriers are the holes. Yes, P type means what? Holes are majority carriers and they are shown in the body. The body is grounded and a voltage is applied to the gate. Body is grounded. It is connected to ground and we apply some voltage here. So gate oxide is an insulator. Therefore, no current flows from this layer to this layer because it is an oxide. Oxide is merely behaving here as an insulator. So in figure below, a negative voltage is applied to the gate. So there is negative charge on the gate. So initially VG is less than 0. Less than 0. What do you mean by that? That means the voltage which you give here, or in other words VGS is less than 0 means what is the value? It is nothing but negative. So negative voltage means it can be -1 or -2 or -3. So when you are giving negative voltage, what happens in this region or in this area? It is rich in negative ions, negative charge carriers. So your polysilicon is almost rich in negative ions. But what is present in your body or substrate? Positive ions. So what happens? What is the influence because of negative charge carriers and your positive ions in the bottom layer? There is a tendency for this negative charge carriers and positive charge carriers to get attracted. So this is the second stage. But before that, so when you look into this, please read this. A negative voltage is applied to the gate. So there is negative charge on the gate. Yes, agreed. The positively charged holes are attracted to the region below the gate. What happens? If you notice, they are scarcely placed. They are very far placed ions. But when you look here, most of the ions, they are attracted towards this and they are aligned properly. Positive charges or positive ions are attracted and they form a region which is just below the oxide called as accumulated. Positive ions are accumulated and this stage is called as accumulation mode. Next stage. Now what happens? Instead of giving negative or first stage, so what happens in the next stage? A small positive voltage is applied to the gate. So VGS is given a small positive voltage. So VGS is given a small positive voltage, and that voltage you still have the tendency to give the voltage as positive, but still what is the condition? It should be less than the threshold voltage. It should be less than the threshold voltage. What is the threshold voltage? It is the minimum voltage required for the device to go into on condition. So when you have the positive voltage being applied to the gate, what happens? The gate which was negatively charged will now become positively charged. Yes, can this happen? Definitely it will happen. And what is the status of the body? Here you find positive ions. So this is also positive, this is also positive. There is a repulsion. There is a repulsion between these ions. Positive ions on the gate and positive ions on the hole will get repelled and they move farther. And what happens? This region becomes depleted. It is empty. It is depletion. It is an empty region. So this is called as depleted region. So when VGS is given as gate voltage such that it is less than the threshold voltage. What is the threshold voltage? The threshold voltage for NMOS is given as standard. We have to follow the standards as per the design. It is given as 0.2 VDD, irrespective of what is the drain supply voltage. If you have it as 5 volts, 5 into 2, 0.2, 5 into 0.2 is equal to 1 volts. So you have to give the voltage such that the gate voltage is less than 1 volts. An example. And please remember suffixed N. This is for your NMOS device. We are considering NMOS device because it is constructed on a P substrate. Similarly, what is VTP? VTP, threshold voltage of your positive PMOS device, is given as minus 0.6 VDD. 0.6 VDD. So let us not worry about this because we are not taking most of the times PMOS. All the while our study lies with enhancement and NMOS device. So not to worry about this. These are all the add-ons. Please remember this. But first stage, what did you see? When your initially voltage is 0, no channel is formed. Second, when you give positive voltage, initially you give negative voltage, that is VGS less than 0. And what happens? The charges are negative in the polysilicon region and as a result they get attracted, and that is called as the accumulated voltage or accumulation mode. Second case, we give the voltage VGS such that it is positive and such that it is less than the threshold voltage. Therefore, positive ions are formed and the positive ions in the substrate layer repel and a depletion region is formed. Next, when a higher positive potential is given, more voltage such that it is greater than threshold voltage. Earlier, how much did we give? Less than 1 volts. Now, threshold voltage is 1 volts. So, give the gate voltage much greater than the threshold voltage. Let us say 1.5 volts. As per our calculation, we got VT as 1 volts. Now, give more than 1 volts, that is 1.5 volts. Now, what happens? When it is more positive, more negatively. So please remember one more point I forgot to tell in the initial case. Your substrate is rich in positive ions. That doesn't mean that there are no negative charge carriers. Few negative charge carriers are also present, but majority will be positive. So whatever leftover negative charge carriers are present in the substrate, they get attracted to the positive ions which are present here. And that too when it is a bigger voltage, not unlike in the previous case. Previous case it was very small voltage, so they just repelled. But now more strong voltage is given, therefore negative ions get attracted and the region below this oxide is actually positive, but it is formed with negative ions. Therefore it is called as inversion region. So the depletion region is also called as inversion region. This is how it happens when you give negative and positive and more positive higher voltage, and 3 different stages you have seen. Now we see an NMOS transistor, gate to source voltage is less than the threshold voltage. So no current flows. Yes, agreed. Therefore the device is off. That first case when we discussed. Now second case we give slightly. So if you look into the characteristics, if I take like this, this is your threshold voltage. This is your threshold voltage. So in the initial case, your voltage is almost negative. Your voltage is almost negative. It is lesser than your threshold voltage. So this complete region when there is no conduction of current is called as cut off. So this is where we are here. We say the transistor is off and this mode is called as cutoff region. Gradually, as the second case goes on, when you give positive gate voltage, accumulation mode, and then you have the channel being created. So let us look into the second slide. Please remember this. This is your cutoff. Then your characteristics is like this. It goes on and finally it saturates. So this region, now only I am telling you, just remember, again I will tell you. So this region is showing the characteristics as linear. So what do you mean by linear? This voltage VDS, the x-axis is VDS and your y-axis is your current ID, drain current. So how much, it depends on what is the voltage you apply, depending on that the current flows. So this is your linear region. They are proportional. The current and the voltage are proportional, and this is your linear current. And after one stage, irrespective of how much ever drain voltage you give, this becomes saturated. So this happens with one gate voltage as reference. So this is how the characteristics goes on. Right now we are in the initial stage of cutoff region here. So this is where we are now talking. Look into the next slide. If the gate voltage is greater than the threshold voltage, an inversion region occurs. Yes, we have discussed this. Okay, creating a conducting path. So you have a path, but still it is not ready. Transistor will turn on, current doesn't flow. It's ready to work. The potential difference between the drain and source is VDS is equal to VGS minus VD. Yes, definitely the difference will be there. And next, as you give more, okay, once you have the positive voltage, gate voltage being greater than the threshold voltage, slightly apply little drain voltage. So the drain voltage is applied here, and slightly when you apply the drain voltage, what happens, there is positive ions at the drain junction, and slightly the region gets depleted here. It gets attracted and the channel gets opened up. So the channel gets opened up because this is your N type. This is also your N type, negative charge carriers. This is also negative charge. So there is a flow of electrons from this region to this region through this path. So this is how it goes on. And next, when you give more, initially, first small positive voltage, small current flows from drain to source, and this mode is called as linear or resistive or triode or non-saturated or unsaturated. So small current flowing from source to drain is called as linear region. So I have already told you what is linear region. Irrespective of whatever is the gate voltage, how much is the drain voltage you are applying, that much of drain current flows here from source to drain. That is called as linear region. And next, when you give greater than VGS greater than a bigger voltage and VDS slightly less than VGS minus VT, then what happens? More of, look at this. So when you give a drain voltage little greater than VGS minus VT, more of positive voltage is here, more of positive charge carriers are repelled here, and as a result the region becomes pinched off. The region becomes pinched off. More and more positive charge carriers, more and more positive voltage will make them repel, and this region is depleted, and as a result this region becomes pinched off. When the region becomes pinched off, no electrons flow from source to drain. No, this is cut, completely cut. So what happens? How much is the current flowing? Whatever was the earlier current flowing, the same current flows here. It is saturated. So this is your saturation mode. So this is how the three different stages of an NMOS device works. So basically we are into the first stage of accumulation mode, then it goes to inversion, and finally it goes to linear region, and then finally it goes to saturation. So this is how an NMOS device works.